today is the topic of refraction. Okay? Now, refraction, it sounds like reflection. They're different things. Keep that in mind, okay? When you speak or when you say these words, make sure you emphasize the correct pronunciation. Refraction, not reflection. So, refraction, first of all, it exists when you have a light wave or an EM wave that travels through some medium that can permit it to travel through, such as light going through a window, okay? So if you have like a light wave that goes through glass, it's going to have refraction involved. Almost all surfaces have some sort of reflection, except obviously for, as we said yesterday, like this lab table. Because the lab table, the color is black, it absorbs all the rays of the spectrum. So light will not be reflected off of here. Okay, so we have some exceptions, but for the most part, everything's going to reflect a little bit, but not everything is going to refract. For example, this cabinet over here does not refract light. To refract light, it needs to permit it to go through. And clearly, light does not go through this wood. But when you have glass, it does. Okay, there are differences. Helen?
Oh, so this table is black.
Mm-hmm.
You can see your reflection in it.
Because you're seeing like the reflection off the gloss that's on here or the finishing that's on it.
Oh,
but the color black itself is absorbing everything.
Oh, okay.
But there's a finish on top of it. That's like even things like tiles that when they polish them, you can see a reflection a lot of the time. You're seeing stuff still. It's reflecting though no colors, whereas the floor is reflecting the white-ish color, whatever color that is. You know, on the tiles. Like this chair is reflecting the blue color. So everything reflects light except for the color black. It absorbs all of it. But the polish or the finishing is what you're seeing the reflection.
Okay.
Steph?
When you buy tights, is that what, I don't know how to say it. Is it opaque or opaque?
Yeah, opaque. It does not permit light. Exactly. It's the opposite of transparent. So transparent permits some rays through it, whereas something that is opaque does not. Okay?
So opaque is dark tights.
And then there's
Sure, which is not permitting light through.
And refraction is...
Well, you would call that transparent.
Oh.
There's transparent and there's opaque.
Refraction.
Transparent permits light through it, so there can be refraction. Opaque things do not permit light through it. There is not refraction.
So those things allow refraction to happen.
Correct.
Wait, what about like translucent? That's
Translucent?
like partially, right?
I forget. I don't know. What's
I think it's in
translucent?
the middle.
Translucent's like nude.
It's no, it's transparent is you can completely see through it. And then opaque is like you can't see at all.
And then translucent's half and half, maybe?
Like lucite
I don't
plastic.
Yeah, I don't know. All right, so let's keep going. First, so we're gonna. That's the first objective, to recognize when it occurs. Second is to identify which way the light's gonna bend. Okay, when it passes through the medium. And third, we're going to use what's called Snell's law to determine the angle or index of refraction.
Snell's.
All right, so let's get first. Our definition of refraction is going to be the bending of a wave as it passes at an angle from one medium to another. Okay, underline at an angle, please. That's the key here. If it's not coming through the original or coming into the second medium at an angle, it will not bend at all. And I'll discuss that in a minute. So again, refraction is the bending of a wave as it passes at an angle from one medium to another. In this case, medium, you could think about material. But we say medium because air is a medium. But you don't think of air as a material, right? Like material is like an actual physical substance you can hold. Whereas air, we don't really think of it as a...
I don't think of a medium as a material. Medium
That's what it is.
means something in the middle. Wait,
Medium has many definitions. In physics, for the sake of this, medium is the material that is passing through. So like a sound wave can be transmitted through a medium of water, through air, but a sound wave cannot be transmitted in the medium that is a vacuum. Okay, but a vacuum can transmit light waves or EM waves. So again, medium is what it's transmitting through. Theta I is going to be used to denote the angle of incidence, meaning the incoming angle. Similar to yesterday, we called that just theta. Okay, then some of the light gets reflected, some of it passes through. When it passes through, it's passing through at a different angle, theta r. And we're going to call that the angle of refraction. Okay, and I'm going to go over these diagrams in much more detail now. Okay, but just draw yourself a little sketch. I'll give you another minute or so. Draw yourself a sketch of what's going on. And it's important to denote the fact that this one starts in air and it passes into glass, whereas here it starts in glass and it passes through the glass into the air. Okay? It's important to know the difference
Should
in
we
the
draw
two
that?
of them. Yeah, draw yourself a little sketch.
A little sketch ball. A little sketch or
Whatever size sketch you would like.
wait, I don't understand. So it goes some of it goes into the glass, but some of it like some of it goes off.
You definitely understand it because that's exactly right.
I didn't know what I was picking up from this little diagram.
That's we're gonna go over it. Alright, so several things to notice. First, as Helen just mentioned, the light ray comes in here, it hits the glass surface, this boundary right here. Part of it gets reflected, but part of it gets transmitted through it because of the fact that it's a transparent material. So this part goes through, this part gets reflected. Now, from yesterday we know that the angle coming in is the same as the angle going out. Okay, so we could even similarly write that this theta is equal to the same as theta I, the theta that's here, because that was from yesterday's lesson. We said when it's reflected, the angle is the same. But for refraction, that is not true. Okay, the reason it's not true is as follows. The light wave travels at different speeds when it travels through different mediums. So when it's traveling through air, it's traveling at the highest possible speed it can travel, the speed of light. But when it hits glass, it slows down dramatically. The slowing down causes the waves to actually kind of push together. And what that happens as a result of that is the angle at which they're moving changes. Okay, so this angle that you're seeing here, this theta r, you can clearly see that it's different from theta I, right? Is that obvious right away or no? Just from the diagram you're seeing on the board. Theta I in this part, okay, is bigger than theta r. And over here, theta I is less than theta r. Okay, and that's supposed to be apparent by looking at the diagram. Again, this angle might be like, if I were to estimate, I'd say this is 45. And I say this is about 20 at most. Okay? And here, this is about 20, and this is about 45 now. It depends on which way it's moving. Okay? So when it goes from a high speed medium like air to a low speed medium like glass, the angle of refraction is going to be less than the angle of incidence. So what's happening is this. The angle, or the rays coming in, and it's bending it toward the normal. Bending it toward the normal.
Wait.
So when it goes from high speed to a lower speed medium, the wave bends toward the normal. That's what you're seeing here in this left diagram. The wave angle here might have been like 45, and now it's only about 20. So it's bending it toward the normal. As opposed to when it goes from a low speed like glass to a high speed like air, the opposite happens. Instead of it bending toward the normal, it bends away from the normal. The angle increases. So in the second case, theta r is bigger than theta I. So again, your rule or thing to remember is when it goes from high speed to low speed, okay, it slows down the wave, which makes it bend toward the normal. When it goes from low speed to high speed, it speeds up the wave, which causes it to bend away from the normal. What's the normal? I see your hand, but what's the normal? Helen?
The line that's perpendicular to the ground.
To the surface, good, the ground, very good. This dashed line here, this vertical dashed line is the normal. It's perpendicular to the surface, okay? That's what we're talking about. We mentioned that yesterday when we talked about reflection.
Is like the theta the same for air and both scenarios? Does it stay
Oh, no,
the
that's
same
just-
when you're in the same area?
It depends on the way the angle of the light was coming in. That's completely independent, yeah.
Okay. Why is it going towards the normal? I don't really understand that. Like it's coming in. So what? You would think like if we say sun, the sun is coming in like on an angle, I guess. Like on a
Yeah.
situation. And
Sure.
then
It hits the transparent object,
why
which slows down the wave. When the wave slows down, all the waves behind it are going to like push it a little bit more. Because all the waves that hit the glass start slowing down. Okay? But the waves that are still in the air are catching up to it. Which what happens as a result of that is the waves that are catching up push it toward the normal. So-
push it. What are
It's hard to, I think, to give you an example just
How
by
about
showing you
in
here.
reverse? How about in the reverse?
Okay, so these waves are going very slow. It hits air, and then the waves fronts get much further apart. It starts speeding up.
Oh,
So when
they're
it
like
speeds
stopping. Okay, I kind of get that.
You know what a good example is like if you have you ever taken, this is completely random, you probably
I'm
haven't.
thinking like a car, like a little car, like an amusement park.
I don't know, not a really.
If you start going really fast, then like I feel like the ones behind you like catch you. Like not even an amusement.
But they're all
park, like,
connected and
anything.
stuff. It's
I don't
different.
know, but like I don't really.
Let me
know,
give you an
like,
example.
I have like a.
If you have, imagine you're on the sidewalk, and the street is next to you, and the sidewalk is elevated a little bit, okay? And you take a barrel on its side, and you start rolling it on the sidewalk. So you have like a garbage can on its side, and you're on the sidewalk and you're pushing it. Now, as soon as the barrel starts to fall off the curb, what do you notice happens? It starts to tumble and angle that way. Ever done this before? I know it's not apparent. But if you think about it, if you start rolling the cylindrical object, as it starts to do it, it's going to tip over like this. And I'm trying to show you here. You have a cylindrical object that's on the sidewalk, okay, and it's rolling forward. The minute it starts to go off the curb, it's going to start to turn like this. You see how it's turning?
Yeah.
Okay, it's the idea of the angle changing because of the rotation. In this case, it's a little bit different, but it is analogous toward that.
Oh, so like if it's like rolling this way, it's gonna hit something, and then start rolling the opposite way, going that way.
Well, it's just that, like, here,
I get it. Yeah, I get it.
I understand that too.
when it's rolling on the curb, it's got, like, some sort of resistance. Then it starts to roll here, where it's in air, and it's going to start to turn off like that. That's that angle turning off. That's what this is right here. I would recommend, the book tries to describe it. It doesn't do a really good job of it, to be honest. Okay? The easiest way to see this is to physically see it, and we're going to do a lab next week. Okay, at some point. It might, for your class, it might be the week after, actually, because of the 3-day week. But we're going to do a lab, and we're going to do a lab on refraction, reflection, and take a look at these rays and what happens. And, I mean, one of the ways you can see it is, again, that example from like being in a pool or in a body of water, and you notice that the person's body looks kind of staggered, or things appear closer. It's because the waves are being refracted. Okay? All right, let's go on to the next thing. So, we need to, before we get to that actually, let me notice one other thing. If a wave comes in, and I'm going to draw it in green. If a wave, God bless you. If a wave came in and it was parallel to the normal, like this. Okay, say the wave came in like that. Comes in parallel to the normal, it's going to go right through. So again, that's why I underline at an angle. If something comes in and it's not at an angle, if it's parallel to the normal, it's going to pass right through and it's not going to bend. Okay? So if you took a flashlight and you held it so that the waves were going straight out through a pane of glass, it'll go right through. But if you angle a little bit, the pane of glass will make the light change.
What's the normal when it's on its side?
What's what?
What's the normal when it's on the side from the center?
So if you had like a piece of glass like this,
yeah, is it
the
from
normal
the
is
center?
coming out of it this way.
But
Coming
from the
out.
center?
It doesn't matter where, as long as it's perpendicular. Here's a normal, here's a normal, here's a normal, here's a normal. Depends on where the ray is hitting it, but the normal just means it's coming out perpendicular to the surface.
Okay.
So anything, the easiest way to remember what normal is, buildings. Buildings are built normal to the ground. And think about that logically. Here's the ground, here's the building right here, right? Isn't this a good analogy? This is the building right here, and this is the ground. This is built straight up from the table. It's perpendicular here, it's perpendicular here, here, here. That's what normal means. Think of a building coming out of the ground.
So just perpendicular.
Can you say like normal force?
Absolutely. That works too, and we discussed that. I'm trying to give more ways to think about it.
What this means perpendicular? Like it's
But perpendicular to a surface, It's like a three-dimensional perpendicularity, as opposed to where you have two lines that are perpendicular. Here, Gabby.
coming out would be normal.
This is perpendicular, two lines that are perpendicular, right? This is a surface with a ray coming out that's perpendicular here, perpendicular here, perpendicular here. It's perpendicular in every direction. So this is called normal, okay, when it's perpendicular to a surface. All right, let's keep going.
Mr. Howell,
Yeah.
when there's a hill, say there's a hill, like slight slant to the ground, they don't build it perpendicular to that because then we have buildings that are like and like that. So,
But you
what
even
do
know it's
they
ground
make it
first.
perpendicular to?
They make it perpendicular to the levelness of the earth in that area. Nothing is really level, obviously, right? The earth is spherical, so everything is curved. The land that we're standing on, I know, weird, right? The ground we're standing on outside is not flat, ever. Even if we think it's flat in that small region, that's where calculus comes into play. You think about like a small region of the Earth, you could think of that or approximate it to be flat. But if you look at that on a global scale, it's all curved. So everything is built really not normal, but in a small level, if you're looking at like just this square city block, you could think of it as being flat. Okay? It's kind of weird, but what they would do on a case with like a hill, if there was a steep incline, they'll reinforce one side or they'll build up one side so that it's more perpendicular to the actual gravitational pull.
Oh, gravitational pull, that's what it's perpendicular.
Well, it'd be parallel, sorry, to the because gravitational pull pulls straight down, so we want to build straight up. So it'd be parallel, but in the opposite direction.
That's what I'm saying.
Helen.
Aren't like skyscrapers built like bend though?
They're built to vibrate for sure, absolutely.
So they don't tip over. So it's not
And also because the ground, there's earthquakes all the time, we just don't feel them. Because they're so low on the Richter scale, the seismic waves are very low, you don't feel the trembles. But buildings can feel them. So like there could be like a mini earthquake nearby, very, very small that we don't even feel, but the building is meant to fluctuate. I mean, think about it. With all the people walking up and down the stairs, if this building couldn't vibrate on its own, it would crumble. It's made to vibrate. Okay? It's made so that it can withstand some sort of swaying. Just like the wind is going to cause buildings to actually sway. They'll sway little, deviations of like millimeters, they will, but it's very little. Okay? It's almost negligible. Okay? So, the next thing we need to define is something called an index of refraction. Now, the definition is my definition. The book doesn't give one, okay? So I would use this. It's a ratio that compares the speed of light in a vacuum, that's this C right here, to the speed of light in a given medium. So like say the speed of light when it's traveling through glass is different. C is the speed of light in a vacuum. Okay? V is the speed of light in a given medium. So it depends on the medium. We don't know what that is.
Alright, this is like a little off topic, but we'll be quick. Say you were in on a planet with no gravity and you were able to like live on that.
Not possible, but go ahead.
Yeah. Would it be like literally so you run for like miles and not even like feel it like that much?
Theoretically, sure. Not possible. Any object exists. Every object has gravity, right? We talked about this. Even this, everything has gravity.
If we could live somewhere with no gravity.
Yeah, you would not get tired nearly as much. No.
Can't you make an environment
That's-
that has
What if it's that too?
No, everyone would be so skinny.
How would you run?
You could literally go run 20 miles and you would barely feel it because there's nothing pulling you.
No,
Yeah, but you
How would
at the same time, you're not exerting force, you're not working your muscles, so you probably end up gaining weight from that.
Yeah.
It'd be like kind of both.
That's a perpetual.
What is that?
I don't know what the answer is because it doesn't exist.
Wait, can I know
Tom.
what
So
that
since every object has gravity, how come like when you see like all the stories and like movies and stuff when
Oh, no, that's
astronauts
space.
like detach from the space station, won't they like float towards it because it's bigger gravity than them?
Well, here's the thing. When you're in outer space, the gravitational pull from a spacecraft is not nearly as high as like the sun pulling you. So you're not going to be pulled toward that
Even though the
spacecraft.
sun is like really, really, really
Wait, so if you
Yeah,
sat in
really,
space,
really,
would
really,
you
really,
eventually
really
be
big.
pulled to the sun? If you could live like without food and stuff.
Eventually, you'd probably be pulled to the nearest large object, actually. So like, say you were near the moon, you'd probably be pulled to the moon before the sun because you're closer.
That's so cool.
Depends. There's a lot that goes into that. There's a lot more than just that. And
What is the variable for
N. So N equals
Like a
C over V. So again, N is the index. Now, here's the thing. N is an inherent property of a material. For example, like density. The density of water does not change. The density of water is the density of water. The density of this tabletop is a certain value. The density of steel, the density of aluminum, they have values. The index of refraction for different transparent objects are given. So like diamond. A diamond has a certain index of refraction, which is why everybody wants to buy diamonds because they sparkle. They have a very high index, which traps the waves and makes them sparkle. And that same thing with cubic zirconium. Cubic zirconium is like the knockoff diamond. Well, that does the same thing. It's able to trap light very easily. So people buy that instead of diamonds because it looks like a diamond. It gives the same sparkle to it. Okay? Obviously, there's tests you can do to show if something is or is not. But the index of refraction is a material property. It depends on the material. Okay? Now, we're going to talk about it in tables in a minute. But let's take a look. For the sake of our numbers, what is the speed measured in for the speed of light?
6.67 times.
What is it measured in? What are the units?
Meters per second.
Meters per second. What's the units of this?
Wait, what is that? V?
V or speed or velocity.
Oh, meters per second.
So what's the units going to
None. No units.
be? So this is unitless, like mu.
Whoa.
Okay, it's unitless.
Wait, so what is C? The speed of light?
Yep, it says it up the top. Okay.
Speed of light in vacuum.
No unit.
Speed of light in a vacuum is C. Speed of light in a given medium is V.
Oh, okay.
Okay.
Yeah, sorry.
You're really not going to use this formula much because you're going to be given the values of n, and we're going to use Snell's law, which avoids using this formula. But this is the relationship of where n actually comes from. Okay. Next thing to think about: you cannot exceed the speed of light, so the numerator is always going to be bigger than the denominator. Okay. So this fraction will never, ever be less than 1. This will always be 1 or greater. This will always be 1 or greater. Because you cannot get a number bigger than C. So the denominator can get up to C. Okay, if it's traveling, say, through air, because air is very close to being a vacuum. It's not, okay, when it comes to speed of light. So this V value could be close to 3 times 10 to the 8, but it's never going to get there. Okay? So this quantity is always going to be 1 or greater. Okay, it's always going to be 1 or greater.
Oh, but it can't be like point something. It can't be
No, it will never be a fraction. It will never be a decimal less than 1. Because the denominator would have to be bigger than the numerator for that to happen. Right? How do you get a decimal?
Yeah.
You get a decimal when the denominator is bigger. But V can never exceed C. C is the speed of light in a vacuum, and is the largest amount you can ever have for a speed.
So C will always be
Okay.
greater than
And
1.
will always be greater.
N will always be greater than or equal to 1.
Why is the speed of light in a vacuum the greatest thing?
That's a whole nother discussion for a whole nother time. Sorry, not to knock you, but we need to keep going, and that would be a whole other... We go off on tangents for a while.
Stay relevant.
All right, let's keep going. It's a very good question.
Stay knowledgeable.
So, here's a table, and you do not need to memorize this table. You'll be given the values if you need them, or in the test, I might just put the table at the very end of it. Okay? So, sure. Now, what you need to notice are several things. First, the value of n here for air is so close to 1, because remember, n is the ratio of C over V. And I was saying that the speed of light in a vacuum is very close to the speed of light in air. It's not exact. For the sake of our class, when we talk about n for air, we're going to assume it's just 1. Okay? So again, you should probably write that one down. N in the air is just going to be assumed to be 1. Okay? And you'll see this all over the place. Now, if you were doing calculations, and you were, say, a scientist in a lab, you would go to a lot more decimal places, right?
Wait, it's also
Okay.
carbon dioxide too. Is that also assumed too?
We're not going to be passing through carbon dioxide, so don't worry about it, but you could say the same, yeah. Now, take a look though. This is what I was talking about. Take a look at diamond, and then take a look at cubic zirconia. Okay, those values are much higher. Okay? They're much higher than anything else there. And what that causes is it to refract the light even more. Okay? Refract the light even more. And what you'll have, okay, what you'll end up getting here, and what we can say is that the higher the value of n, okay, the higher the value of n, the more refraction is involved. Okay, the more refraction is involved. So the light is bent closer to the normal. So let's say as
Refraction.
n of the medium, not air, as n of the medium increases, okay, you have more refraction, which causes it to bend closer to the normal. So theta r decreases. Okay, again, I'll move it up. I know you can't see, sorry. Okay? As the value of n in the medium increases, it's going to cause the light to refract even more, which will get it closer to the normal, which makes theta r go down. Remember, theta r is the angle of refraction after it passes through the medium. Okay? So for a diamond, what it does is it actually ends up trapping the light. It traps the light inside of it, which causes it to sparkle. Okay, that's what's happening there. Because the value of n is so great, it could refract it a lot more than any other medium.
Since we have the opposite diagram where it goes from glass to air, would it be the reverse then?
Yes, and the same thing occurs. So if you went from glass to air, okay, it would cause, the angle would increase more than it would decrease or go away from the normal. Okay? So these are values that we're going to be using. Okay, we're going to be using these to calculate certain things. Anybody know the time for this period so I have an idea?
It's like 4 minutes.
Several things to note. Okay, several things to note when looking. Whoops. The liquids are given at temperatures, and so are the solids. The gas is at 0 degrees Celsius. It's not going to affect our problems. we're not going to go into that, okay? The other thing to notice is solids at 20 degrees Celsius, but ice is always at 0 Celsius if it's a solid or lower, okay? So let's take a look at an example of this, but first, let's take a look at Snell's law.
I don't understand what's the temperature, just so it's to decipher if it's a solid.
Yeah, the temperature when the temperature changes, these laws are going to change. The end values change. So we're making the assumption that we're at a constant temperature. Because temperature, pressure, a lot of things actually affect this. But going into all those would be like tons and tons more equations to go into beyond this. This is like a simplified college physics version of it. You know, if you were a scientist, you need a lot more to it than just this. So here's what Snell's law tells us. Okay, Ni times the sine of theta I is equal to Nr times the sine of theta R. Okay, Ni, theta I, Nr, and theta R. I stands for incident or incoming ray. You could call either one. I don't care. R stands for refracted, not reflected, refracted. Okay, Steph?
Could you kind of think of it as initial and final?
Sure. Yep. No problem.
That's basically what it is?
That's exactly what I think. Yep.
Okay.
Okay. Initial is like before it hits the surface. Final is while it's inside of the medium. Okay. Keep in mind though.
Inside the medium,
Yeah.
not like outside.
So this is what's happening, guys. Keep this in mind. Ready? Let's draw in a little image of this. Whoops. Whoops. I didn't mean to do that. Hold on. Let's draw a little image. So let's say we have a window glass pane, and this is glass. Okay, this is air, and this is air. Glass has a thickness. A lot of glass panes are double paned. And if you want to learn more about double paned glasses, you should watch the video online about heat that I put under extra videos for SAT physics. It talks about why windows are double paned. Now, what happens is this. The light ray is going to come in at some angle. It's going to hit the glass and it's going to bend it. So here's the normal right here. It's going to bend it closer to the normal. So instead of continuing in the direction that it was lined up, like if it continued the ray, it would continue this way, right? Okay, but it's not going to. It's going to bend closer to the normal. But then what happens, after it hits the glass, it bends back. So this one is going to end up bending back outward. So what happens is, when light travels through a medium, when it's in the medium, it gets bent, but then when it passes back into air, it gets bent again. So this is the example we saw in the beginning from air to glass. Then we did from glass to air. Put it all together. So it comes in at some angle from the air. Let's give numbers. Let's give numbers to make it easy.
Mr. Howard, that other line, is there another line that's...
Now this other line was just saying if the ray had continued. Okay, if the ray had continued. Try and listen, guys. I talk while I write it. That was as if the ray continued through on a normal path and it didn't get refracted. Okay? So let's say that was 30 degrees to start, the first angle. Then the second angle would be something less than 30. Okay, let's say for the sake of this 20. Okay, let's say 20. It could be 10, whatever. So that angle is 20 in here now. Okay, this angle here is 20. Then what's going to happen is, this angle out here, if we redraw the normal, okay, because now the normal is moved. Okay, here's the normal now. This angle is back to 30. So what happens is refraction occurs inside of a medium. It doesn't occur and stay that way. So when you pass from air, which is high speed, to glass, which is low speed, the angle bends toward the normal. So it goes from 30 to 20. But then when you pass from the glass to the air, it goes from low speed to high speed, so it bends away again. So it now goes from 20 back to 30. Okay, so you have to remember, every time you change medium, you're going to have some angle change. So when we see light come in through the window, we don't see that it bends, because it bends in the glass, but then it rebends when it comes out to the air here. So we're not seeing that bending. But if you look at a pool, you have air and you have water. So you're seeing the bending in the pool. All you have are the two surfaces, air and water, two mediums, air and water. You don't have it passing out into air again. So when you look in the pool, you clearly see the refraction that occurs. Whereas when you look in a glass window, you don't see it. Because it goes into the glass and it bends, but then when it comes out of the glass, it bends back out. So you're not seeing the effect of this, actually. Okay? Emmett, you had your hand up first. You good? Can answer? No.
Wait for the normal, the line normal.
The normal can be anywhere. The normal could be here.
Why did it move?
The normal could be
Why
here.
did that move?
Could be here. Could be here. It moved because the wave slid it over. Okay?
So it will be like we're
Wherever
changing
it-
normal to whatever the point is that this ends at?
Exactly. So this touches the surface here. Let me use the marker so everybody can see that's recording. The first wave touches the surface here, so the normal is here. Then it gets refracted, so now it hits the next surface here, so now the normal is there. If there was another surface, okay, down here, and it hit it right here, then the normal would be there. The normal is just a perpendicular line anywhere along the surface. So the normal could be here, it could be here, it could be here, it could be here, it could be here. Those are all normals to the surface. It just means perpendicular, that's all it is.
Alright.
Erica.
I have two questions. So the normal isn't changing from like where it starts, right? So if you're basing it off of that, the normal isn't changing with the way that it's going.
The normal is always perpendicular. It can slide left and right.
Alright, and then is it being like is the angle changing inside the glass?
But not really.
I'm sure it's not. Go ahead.
How is light?
Listen, gentlemen.
How is like light actually created?
How is it created?
Or like for like God? Like how is like forming the light?
Well, the light that we see is caused from like a filament, and like it depends because like a long time ago you had filaments in bulbs and you had this gas around it, usually argon, and it actually had a chemical reaction that caused the light. Now we have these incandescent lights and fluorescent lights and all this other stuff. I don't know too much about those. The sun is like a nuclear reaction going on. That's what's happening. It's like imagine just nuclear bombs going off, giving off this radiation and this source of light. That's what we're seeing over and over.
And also, do you know how the projector has an angle that's really perfectly flat on the wall? Why is it not like kind of like
Skewed?
yeah.
Because the actual opening up there is made so that it fits perfectly. So instead of it being perfectly rectangular, it's actually different because it's coming down at an angle. Yeah, they make sure that they look at these things ahead of time. Yeah, exactly. It's shorter on the bottom than the top.
How do they know where on the ceiling it's going to be?
Because you can make the
You can adjust it. You can adjust the height of it. So Mr. Richroth probably adjusts. There's probably a standard also. The angle or the... It could all be, there's settings on there that could adjust the screen. So you could adjust the top and the bottom width and stuff. Yeah. So, he's talking about projector, yeah. Alright, so let's draw a picture.
I didn't say it was.
Okay, here's what you need to be thinking about. I would draw it, yeah. Okay, that's what we've got right now. That's all we have so far. It's coming through air. It hits the surface at an angle of 25 degrees to the normal. Remember, the normal is vertical. And it's quartz that it's passing into. Now, we have to know two things first. Remember from yesterday what I said about air. We can assume air is like a vacuum. We can make that assumption. So if you remember, N from yesterday was the ratio of C over V. N for air is always going to be around 1. And if you go back to the table from yesterday, the table it was 1.000 and then it was like 213 or something. Okay? It did exactly what I have written down. It was 1000293, not 213. So for air, okay, we're going to say the N value of air is just 1. From our table from yesterday, and I'll tell you, you'll be given this or you'll be given the table, fused quartz N value is 1.458.
Can we go with what N is again?
N is the index of refraction. The higher the N value, the more light will be refracted. Remember the diamond was the example that has a value of around 2.4. Okay, the light is very refracted, or much more refracted there. Now,
We need to know how to figure that out.
no, the N is going to be given in the table or in the problem. Again, N is in the table or in a problem. Here's our formula.
Wait, what did you just say about N?
Okay? It'll be given in a table or in the problem. So for this problem, what is the thing we are looking for? Raise your hand and tell me, please. What are we looking for, Olivier? Yeah, we're really looking for theta r, but we should solve for sine of theta r, and then we'll figure out in a minute, or we'll talk about how we can get the theta by itself. Some of you know already, okay, and that's fine, I know that. But we're going to go over this.
Wait, I thought you said there's no mathematical problems in the next school.
No, I never said that. I said there's fewer, for sure. Like in chapter 14, there was only really, I think, one formula we used.
Yeah, I think
There are fewer. This is one of the few that we're going to see.
Actually, you remember
Now, this is one of the times that I would actually, once you divide through, okay, divide by NR, you get sine theta r by itself. Here, I would actually plug in numbers, okay?
Is I initial?
Yeah, I is in the incident, and R is the refracted. So Ni is the one up here.
So you think we go about it as initial?
Sure, initial.
Incident's the first half of it, and then okay.
Yep, it's the ray that's
What are
coming
the
in.
other name- Yeah, there's
R
two.
is the refracted.
I don't know, but what's the other names for the incident? There's another name for incident, right?
Put that on me.
Incoming,
Ink.
incident, incoming, or initial. I could stand for all three. It doesn't matter. Jack.
Will it ask for the, will it say, in the question, will it ask for the refraction?
Yeah, ink.
That's what it did ask for.
Okay.
Yep. The problem at the end said determine the angle of refraction.
Oh, okay.
Okay.
Wait, so Mr. Hall, we're solving for theta r.
But for now, let's just leave it as sine theta r, and we'll talk about how to get theta r by itself.
Okay.
This will be good because you'll learn a little bit of a preview for algebra 2. So when you get to this in algebra 2, it'll be even nice and easy for you guys. All right, so let's go through this. Plug in numbers.
25.
Okay, that's what we have right now. This is why you need a calculator. I wasn't joking. You have to use the sine of 25, and then we're going to have to use the calculator again to get theta r afterward. Okay? Make sure your calculator is in degree mode. If it's not, you're not going to get the right answer. Go ahead, Molly.
0.289.
Good. 4 decimals. 4 decimals for this always. Write that down on the side, please. Okay, whenever you're going to do anything with sine of theta and you have to get theta by itself, keep 4 decimal spots, please. And you need to do that, or else your answer is going to be off.
It's 0.2899.
Yeah.
299? Thank you.
Instead of
I thought you said 8, sorry.
Yeah, I was making sure you got the right answer.
So then do you divide by what? How do you-
And that's what we have to talk about now, okay? So, here's what's going on. Let's discuss. Because this can be a little confusing, especially since you guys haven't covered this yet in class. A lot of students have the common mistake to say, okay, divide by sine, I guess, to get rid of the sine, to get theta r. But these are not multiplying. Sine and theta r are not multiplying, okay? This is saying the sine of theta r. It's like f of x. Remember the function f of x? F is a function of x. The sine is a function of theta r. Okay? Now, I know you know. Just give me a minute, okay? I do know. Now, if you remember, and I'm going to put a little side note at the top, so you might want to write this down. Okay? If you had the following. If you had 2/3 x equals, let's say, for the sake of this problem, 8. Okay? And you want to solve for x. What would you multiply both sides by, Max? 3 over 2, because that's the what? The reciprocal. Agreed?
That's right.
Another word for reciprocal is the inverse. So watch. We'd multiply by 3/2. Okay, close, not cosine, but good idea there, Jeff. I like that. And this would become 12, right? So, what we need to do is this. We need to get rid of the sign by using what's called the inverse function. Now, inverse in math is x to the negative 1, if you remember. That's the key on your calculator, negative 1. But we don't want to do that. We want to get rid of the sign. Look at sine on your calculator, and then look right above it. You'll see sine negative 1.
Yeah.
You see sine negative 1 there? Okay? So, what you want to do is the following. You want the sine negative 1. Cosecant is the co-function of the reciprocal function, different. Okay? So what we do here is this. We take, listen guys, stop talking, listen.
Oh, on both sides.
We take the sine inverse of both sides. On the right-hand side, sine inverse and sine kind of cancel out. They don't mathematically, you don't want to say cancel out, but for the sake of this, we'll say they cancel out. And you're left with just theta r over here. Again, these two parts kind of cancel each other out. And all you got to do is do in the calculator, press second sine to bring up sine inverse on your calculator, and then type in that number. Molly.
Yeah, 16.85. Wait, so is that equal? Oh, that's equal to theta r. Okay.
Because again, When you take the sign of something, it needs to be in a degree answer or a degree mode. So when you take the sign inverse of a decimal, your answer units are degrees now. Okay? I'm giving you like a very abridged version of sine inverse and cos inverse. You'll learn all about it in Algebra 2. But what you need to know is that when you have the sine of some angle and you want to get rid of the sine, you do the sine inverse on both sides, canceling out on the right-hand side, and getting some decimal value or some degree value on the left-hand side. Okay? Any questions? Again, it's just, all it is a skill we're developing now. I'm not going into a lot of the detail about it, but I'm teaching you just how to figure out how to get rid of it.
Didn't we say that when light is reflected, the angle is equal? They're both 90 minus.
Reflected. This is refracted. Refracted, yep. Paul.
How do you plug it into the calculator?
Press second, then press the sign key. It'll bring up a sign -1. Again, this is why you should be practicing with me. Press second, then press sign, and then press 0.29 or 2899.
And when we said, you guys said the refracted is
It's what goes through.
ratio between the vacuum and something on
The n value is the ratio of the speed of light in a vacuum over the speed of light in the actual material, like quartz in this case. But the n value you're going to be given. But you should know what it is or how to figure it out, but you'll be given the n. Okay? Now, before... Go ahead, Jack.
I just kind of get a quick
Yeah.
thing.
Before we go on to the next example, I want to point something out. Okay, I want to point something out. In this problem, we are finding the angle of refraction, and it's 16.85, it turns out to be. Okay, 16.85. So what that would look like is this. This light hits the surface, and now it bends, and I want to actually go right against the normal there. It bends it closer to the normal. So this is the angle we're looking at now. Okay, and this reiterates what I said yesterday. It goes from a high-speed wave in air to a low-speed wave in quartz. Whenever you go to a high-speed to a low-speed wave, it's going to bend toward the normal. Okay, toward the normal. Now, if it came back out of the quartz, let's say it was in the air, it was a sheet of quartz, like a glass pane of quartz, and then there was air on the other side again, like this. Okay? There was air afterward. What would happen is actually, it would bend back to the exact angle it came in at, of 25. Okay? And you could redo the problem, and you could solve the new problem using 16.85 here, 1.458, and then n equals 1 at the bottom, and you'll end up getting the angle that it started with. And it'll look like this.
Oh wait, so if you reverse that?
If it went back to air, and that's why we don't see refraction in the sun's rays when they come through the window. Look at the window. It's air on one side, it's glass, and then it's air. So there's going to be a bit of refraction within the glass, but then that refraction counteracts itself when it comes back into the air. Okay, so if you think about something that has 3 layers, there's really no change from beginning to end. There's only a change in the middle. Okay? This is, again, assuming that it's air, quartz, air. If it were air, quartz, diamond, this angle is going to change. We'd have to figure it out. Okay? Max?
If you have like the degrees and everything else, and you find like something about the
Yes, the composition of it. Yep, and that's the next problem. Exactly what Max just asked. So let's take a look. A light wave travels through an unknown medium.
What is it?
Right? We don't know. It's unknown. Now, if the angle hits the medium at... That's right, people. That's right. Come on. If the angle it hits the medium at, with respect to the normal, is 30 degrees, and then the angle of refraction is 12 degrees, then determine the material it passes through. Okay, it's coming from air into some unknown substance, so we don't know it's fused quartz. We have to figure out what it is this time. Okay, Snell's law. 4 things always. It starts in air. So what's Ni?
1.
Yeah.
It hits the angle, it hits the surface at an angle of 30 degrees. Is that theta I or theta R? The angle of refraction, which is obvious, right? Theta R is 12. So what are we solving for? And now, if we can find the index of refraction of the material, we can then go to our table and see which one it correlates to. So if we can find NR, that's the N value of the new medium, and we can look at the table and see what it correlates with. Okay? Go ahead and solve for NR on your own. Go ahead and solve for NR on your own, using your formula, please.
Are we going to be given that formula on the test?
Yep.
In our subject, physics test, they won't give me.
I don't know. Somebody asked that a few weeks ago. I have to look into it still. I've been meaning to. I think that they give you some if they want to on the test itself. Like in the problem, it'll say, the period of a pendulum is 2 pi square root of L over G. They might give you it in the problem. But they don't give you like a table, I don't think, in the beginning.
And so on the SAT, they give like all the formulas for geometry, like all that.
In the SAT math, they give you those. Yeah. But the physics test, they want you to know some things. Like, for example, you need to know that the period is the inverse of the frequency. Tau equals 1 over omega. That's like a thing that you should know, that they are inversely related. I don't think any are given in a table, Fernando, but I think that some of them that they don't expect you to memorize might be given in the problem itself. Okay? So it might say like using Snell's law, blah, 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 determine, okay? So they might give you the formula like that, depending on what it is. And again, this is stuff that you guys should, start looking at when you buy like a practice book for the SAT physics test. You just look through, look at the sample test and see what they give you.
Bruno would know. He carries around. Can you go up there? Can you show me?
Solve for NR, please, algebraically. What are the units going to be? They are unitless. The sine of an angle is unitless. So these are unitless here. Ni is unitless. So NR will be unitless. Jeff, you good at the top?
The one girl has like this really like. Oh. The one girl has like this crazy inappropriate song and like it's hilarious. What? I think it's second place rated. Oh, Adrian. My cousin
Yeah. I did one on my daughter. I was like, yeah, draw a bunch of shades.
This other guy called the one girl was like,
Mosh, what do we got here, Mosh? Listen, gentlemen, come on, stop. 2.405. All right. Now, again, anytime you solve for the index of refraction, it's going to be unitless. If we go back to our table, okay, so I'm gonna go back to our table now. You know it already? What is it? You remember I said it a little while ago. Good. In the table, and I'll show you what the table looks like if I can actually find it. Hold on. So again, diamond. That's at a certain level, and it's also at a certain temperature and pressure. When those things change, it actually changes it also. Your homework for this section. Homework is the following. Page 567, the top of the page, 1 and 3. And then on the bottom of the page, example 4, the two different sections of problems. Okay? The two different sections of problems.
Wait, so if you look at an index of the diamond or whatever, can you figure out mass or something? Or like, I just don't understand what that does to you.
Well, imagine you had some unknown material, okay? But you were able to pass light through it and measure the angle of refraction. Based on that, you can try and determine what the material is or prove that it is a real diamond.
Isn't there like an easier way of doing that, like math?
Yeah, there's definitely other ways to do it, but this is just one method. Max, I totally agree with you. There's definitely other ways to determine. Absolutely. But in science, you don't want to use one way, you want to use several ways. So you might look at a hardness test to test for a diamond to see if it would actually like scrape on metal. You might look at like an example where you want to break it with a hammer. You probably won't. You could look at like a force test. So there's different tests you can use to verify that it is. Okay?